So let's take stock of where we are. We are interested in the probabilities Sn that there is a success run of length 5 at or before the nth trial. And we've just decomposed it beautifully into a sum of probabilities F1 through Fn, where the F's represent the probabilities of a first success run occurring at a certain point. And the question now emerges, well, we've reduced or we've moved the problem from computing S's to computing F's. How does one compute the F's? We appeal once more to additivity. Let's pause and think about what it takes for a success run to occur at the nth trial. Here is a key principle. A success run will terminate or occur at trial n if and only if there is a first success run occurring at some trial j at or before n. Let's think about this again. If a success run occurs at trial n, then either it is a first success run, in which case there is a first success run at trial n, or there is a prior success run. And if there's a prior success run, eventually there must be a first success run, which then must have terminated at some trial j. And so the picture is something like this. For some j between 1 through n, there must have been a success run which terminated at that j. We now have a renewal. The coin tosses effectively begin anew with trial j plus 1 as the first trial, and then proceed on through trial n, where we are told that there is a success run. Of course, the success run occurring at j is the first success run. Following that, we have a new sequence of tosses, as it were, but in that sequence of tosses, we could have one or more success runs, but you are guaranteed that there will be one success run terminating at n. This has broken the problem up into two beautiful pieces. In the first piece, we have a first success run which is occurring at trial j. By definition, the probability of that occurrence is f sub j. Now, what about the second piece? Now, here we have a renewal. The coin tosses have effectively begun anew with a new count. J plus 1 is essentially the first toss in the new sequence, and the nth toss in the new sequence is now the n minus jth toss in the sequence. There are n minus j trials following j and leading up to n. And in those n minus j trials, we find that there is a succession of phi 1s terminating in a success run at the last of those trials. There are n minus j trials with a success run at trial n minus j, and our notation and our terminology tells us the probability of that is u sub n minus j. Notice the trials are repeated and independent. We've got a statistically identical version of the experiment which has been started again at trial j plus 1. And now we've had n minus j trials culminating in a success run. And therefore the probability is u of n minus j. Now let's stitch both pieces together. The key is that the pieces correspond to disjoint trials, and we recall the basic principle of independence. Events devolving upon non-overlapping trials must be manifestly independent. And therefore, the occurrence of the first event is independent of the occurrence of the second event, and therefore the probability of that entire sequence is just a multiplication of probabilities, fj times u n minus j. Notice how elegantly and simply independence and product measure have finessed what could have been a very difficult calculation. Now, what we've discovered is that if there is a first success run at trial j, followed by another success run at trial n, the probability of that is fj times u of n minus j. Now we simply appeal to additivity to stitch together the various possibilities for where the first success run could occur. If it occurred in the first trial, then you have f1 times un minus 1. If it occurred in the second trial, you have f2 times un minus 2. If it occurred in the jth trial, fj times un minus j, and so on. If it occurred in the penultimate trial, you have fn minus 1 times u1. And if it occurred in the last trial, then you just have fn. Of course, all these events are disjoint, and by additivity, once more, un is the sum of the probabilities of the form fj un minus j on the right-hand side. Now, the expression on the right is not friendly. It looks complex. It looks like you've intertwined and mixed things together. Right? But there is going to be a light at the end of the tunnel. To start with, sums of that form are endemic in mathematics, in the natural sciences, in engineering, and in the applied sciences. Such sums are called convolutions. And as you progress through your mathematical education, if you take a course, for example, on transform methods, or you take a course in, let's say, mechanics or physics, you'll find such sums cropping up repeatedly. The idea of a convolution turns out to be one of those basic principles which capture essentially how you can stitch things together, and in consequence, they occur repeatedly in science and mathematics and engineering. They turn out to be a hugely important concept. It's hard to overstate how important this basic operation is. For our purposes, all that history and the context is not so immediately relevant. It's something we just store away at the back of our mind, saying, okay, I've stumbled upon a convolution. But for our purposes, it is simply a manifestation of additivity. The whole is equal to the sum of the parts. And I've got a particular expression. Now, it looks complex, it looks messy, but let's keep our eye firmly on the prize, on the target. We are interested in Fn, the probability that there is a first success run at trial n. And we find Fn appears on the right-hand side of the equation. Let us isolate it by moving everything else to the other side of the equation and write this equivalently in the following form. Fn is given by an expression on the right now, starting out with un, from which you subtract out probabilities of the form fj times un minus j. Okay, it hardly seems like we made any progress, so I just remassaged something and rewrote it, but it's still a clumsy, awkward-looking expression. Can I do anything with it? But here is the key point. Again, we are interested in Fn. What do we see on the right-hand side? Well, we see various values for u, u1, u2, u3, up to un. We also see the values f1 through fn minus 1. And this leads us to our next slogan. If you know the sequence of the u's, u1, u2, u3, and so forth, and you know the first n minus 1 values for the f1 through fn minus 1, then you can compute the nth value for the f. This is the beginning of a recursive calculation which says, well, maybe I can compute the f step by step. First compute the first one. If I know the first one, I know the next one. If I know the next one, I know the next one after that, and so on down like a chain of dominoes falling over. So far, so good, but of course, this seems that we have fobbed the problem off and made a more difficult problem. What now can we say about the u's? Okay, this is our next step.